Hi everybody, this team number 3. The team members, myself, Mohamed Elyamani, Soliman Mohamed, and Dauda Umar Mohamed. And this is a final project that we applied geometric control. And the objective here to stabilize the mobile manipulator using our geometric control. So here, first thing we analyzed the robot. It contains a car, mobile robot here, car, and we deal it here for simplification as a fully actuated car. And here there is a mount, should be attached here, and the arm, and this mount connect this arm to the car to have finally the system like this. So as we see here, the degree of freedoms locally, or and first thing here, we have 7 degree of freedom for this arm, the tool, here the end effector frame, and here the car. So locally for the car here it works at X, Y, and phi. So here also there locally there are here 3 degree of freedom in addition to 7. So the total it is 10 degree of freedom. We analyze the frames to understand the kinematics for the system, starting from the car till the end effector. And also here we saw that the car here, it is in SCE2. This is a manifold for it. So the X, Y, and the psi for this car, it is embedding in this transformation G, and the theta for it is vector for the arm in R7. It is in the joint itself ideally in S1, but it's isomorphic to R. But so the idea here it is isomorphic to R7. So we delete the system in EC2 across R7 as we see here. So the body velocity, it's Vx, Vy, and omega, and the arm it is theta dot. So also the velocity in R10. So first thing we worked on the system in local coordinate chart in the R, but we needed this to convert it to V, and V here it is the body velocity. We need to convert this from special coordinate to body coordinate. So this is only the transformation from the special to body, and the joint itself it is identity. So this is basic. This is simply like this. So from these two equations we got V and V dot. To convert this equation system dynamics to the new one, and that is this equation that we used. Simply this is inertia matrix M, and this is acceleration for in the body, and this is Coulomb and centrifugal vector, and this is a gravity vector, and this is viscous damping. And here we have the input, generalized input, it is in R10. So here we deal it with in identity, but you can see this B, it is like on-off switches. So here, if it is B, it is an identity, which means that all the actuation, all the motors, they are working. And here disturbance. Here in the controller part, we deal it as equal 0, and external range, we deal it also equal 0, and this is the Jacobian to convert from the end effector to the joint space. So the goal here to, after analyzing the system dynamics in the open loop, we want to stabilize it. So this is the architecture that we imagined the system that summarize everything that will come. So here, this is a mobile manipulator and the controller. And for some reason, we will know it works locally. So for this reason, we need another other layer. One of the approaches to solve this to use planar. So we can see this architecture contains two layers, a planar and a local controller. So the first thing here, our system, it is in task space. The controller here should be in task space, not joint space. Why? Because the motivation here, the task space will give us sophisticated solutions. So we started to convert to get here, because here it is in the task space. We cannot make subtraction minus here, but we need better solutions in the geometric way. So we like this, for example. So we should convert these matrices to the Euclidean for the base in R3, and for the arm to convert it also from matrices from desired one to current one, and to get also the sixth dimension. So overall, after stacking these, we have 9 degree or the error. It is now in R9. So okay. So now we want to get the controller. So first we defined our Lyapunov. We need to define good candidate Lyapunov function, and this good candidate Lyapunov function should be positive. Here this Lyapunov function, it contains the kinetic energy for the system and the virtual task potential. And the kinetic energy here, because M here, the inertia matrix, it is positive. This is the identity for the mechanical system. So this part, it is positive. And here we can we need to choose the k greater than 0. So from this we have now positive definite Lyapunov function. And here we use this potential task to imagine that we deal with the task space as the spring between the current and the desired one. So this is the philosophy that we worked with to get the impedance control from this. The next step to take the derivative for this Lyapunov function, and here, as we see here, this is the derivative. So we need to make this derivative to be less than 0 to have a sympathetic stable. So we can play with this torque. And the idea here to cancel these terms to have at the end some term less than 0. So from this, we choose this torque to have v dot less than and equal to 0. But here also we need something else to prove it. It is a sympathetic stable, to prove it also using LaSalle, because it is not less than 0. It is less than 0 and equal to 0.
So we need to make sure it is not stable but asymptotic stable. يعني, which means it will converge to the desired pose. As we see here, we succeeded to prove it. But the problem here, okay, so now we have a good approach to as a local controller, but our motivation not to work is only on a small region, but to stabilize it over a large region. So because the log limitation here, it works only within 1 by, especially for the rotation. What if there is aggressive the motion or the error more than 1 by, or it is the motion it is large? So this will be not valid. So the idea here to use a planar to convert this large error between the initial to final one to very small steps, and at each step we have a desired pose. So at each time sequence, each time we need to have some pose in whether in SCE3 or SCE2 for the arm or the manipulator. So how can we get these desired poses along to get a smooth trajectory? One of the ideas to optimize over to minimize error for the pose for the arm and the base, and minimize it between each time between two time steps. Here the demo that show for us here how the system works. First thing here, this is GUI that we built, and we first define the initial pose here and the final pose and the planning time here 3 seconds. We can define it, and from this the planner, its job to give us this trajectory, and at each time step, as we see here, the error, because local controller now it is very good, it almost zero, and the Lyapunov converges to zero, so which means that the torque, it works very well. And as we see here from the demo, the planar is smooth, and the system for the arm and the mobile car, it follows very well this trajectory. So there are two trajectories here, one of the car and one for the arm. And this is, as we see here, the trajectory for the End-Effector and trajectory for the base. So we have here two visible trajectories. And we need to respect the trajectory because all of the system they are rigid bodies, so they are connected and under some constraints. So the visible trajectory should respect these constraints. And the results, as we see here. And one of the limitations for the planar, if there is aggressive motion or larger motion, the planar itself could fall in a point it's not good to follow. We see here that local planar that we used needs some improvement in the future to one of the approaches, for example, to use global one. And this is the result that we got from this one. So from this, we saw that the controller work is very well, but we need some improvements in the future to have a better, smarter system. Thank you so much for listening, and have a nice day.